let's say a warm-up word about the steady state solution. We're going to be talking about it in more depth further on, but let's first have a little bit of foreshadowing of what we will be talking about. So we have, in the previous video, built up the solution of the 1D heat equation as the product of two parts, an exponential part and a sign. And without going in depth about what Kn is, we know it's real. We know that the first part, the exponential, is a negative exponential, so it's decreasing exponentially over time. While the second part, it's a sign, so whatever it's in K, it's still something bounded between 1 and minus 1. So every single component has, over time, the behavior of the exponential that is decreasing over time. For t much bigger than 0, this exponential decrease is the thing that is dragging your temperature to stabilize at 0. So 0 everywhere is what we call the steady state solution. It's a solution that doesn't depend on time, and it's a solution of the PD plus boundary conditions. Obviously, it doesn't, because we dropped the time constraint, it might not satisfy the initial conditions. Usually it would not. It only satisfies the boundary conditions and the equation. In this case, it's u hat is equal to 0. In general, steady states outside of the heat equation might be non-unique. In the case of the heat equation, any solution is a sum of a steady state solution and a transient solution. Transient means that it passes over time. You start in some situation and you have a transient solution that brings you from that situation, that initial condition, towards the steady state. And once you reach the steady state, usually at infinity, then you stick there forever. Here, I would like to show you a little simulation of what the solution of the heat equation that we have built is. I have given a parabolic initial condition, and you notice how it starts, the solution at time 0 starts to be exactly the parabolic profile, and it immediately starts decreasing really fast, tending to 0 everywhere. So it starts as a parabolic profile, and then it decreases to 0, and you really see the exponential decrease. Then it slows down a lot, but you can still zoom in and see that you're not at 0 yet. You're going to take infinitely long to reach actually 0, but you're getting there fairly fast on the general scale of the problem. Let's have a fast recap of the steps that we have taken to solve the heat equation. We have looked at a heat equation or diffusion equation. We have set a sum of boundary conditions with either Dirichlet or Neumann or Robin in such a way that the union of the points in which we have applied the Dirichlet, the Neumann, and the Robin becomes the rule boundary of our domain. And we have set an initial condition for every point in the domain. We have taken the case of omega just being an interval 0 to L in R with homogeneous boundary conditions. We have taken the ansatz that u is a product of two functions, x only depending on the space variable and t only depending on a time variable. So we can look at it graphically by putting an initial condition at the bottom of our infinite rectangle, and then everywhere a boundary condition for infinity. And with this ansatz, we can divide our problem into two ODEs. And we can do that by replacing ut by t prime x, uxx by x second derivative t, and shuffling a bit, noticing that we now have t prime divided alpha squared t and x second divided by x. This depends on time and space. So if it's valid all the time, then it needs to be a constant. We stated why it needs to be in the form of minus k squared with k real. And then we have separated our problem into two ODEs. One in the Sturm-Liouville setting, and one a very standard first order ODE. We have solved the Sturm-Liouville problem, finding eigenpairs and using the eigenpairs to solve. So in particular, we use the value of the eigenvalue, sorry, this double word. We use the eigenvalue to set that and use it in the ODE for the temperature. And we developed the ODE for the temperature. Then we go back to our ansatz. We have a component un that is the product of the eigenfunction times the time solution with the eigenvalue fixed. And we can say that the full solution of the PDE is an infinite sum of a coefficient times this component solution. Then we have left with the problem of finding the coefficients of this infinite sum. And these coefficients need to satisfy the infinite sum of the coefficient times the eigenfunction equals to the initial condition. And for the Sturm-Liouville theory, this is well posed, and we can explicitly state that our Cn is equal to inner product between f and phi n divided by phi n divided phi n, with the inner product of between f and g being defined as the integral from 0 to L of f times g. Let's look a little bit more in depth and a little more precisely to the steady state solution. So we have introduced u hat, that is a solution of the heat equation that doesn't depend on time. So we went from having the full PDE, that is the derivative over time of u, minus alpha squared, the second derivative of u with respect to x, equal to 0, and then we have some boundary conditions and an initial condition. And we go from here to writing the problem that is, well, the derivative over time disappears because we want to look for something that doesn't depend on time at all. So we only have minus alpha squared second derivative with respect to x of u hat equals to 0, and the boundary conditions based on u hat. Then we can say that u, our general solution, is equal to u hat plus v. U hat is the steady state solution, the one that solves the problem that we have just written down, and v is the transient solution. V depends on x and t, while u hat only depends on x. What equation does this transit solution satisfy? Well, it has to satisfy the PDE, so we need that delta t minus alpha squared delta xx of v needs to be equal to 0. It needs to satisfy the boundary conditions, trivially though, because the non-trivial boundary conditions are already being taken care of by the steady state solution. And it needs to satisfy an initial condition. What initial condition do we need? Well, it's an initial condition that is based on the PDE, the global initial condition, minus the steady state solution, because the steady state solution doesn't depend on t, so it's going to be there at time 0. You can think about it because you want u hat plus v to satisfy the boundary condition and the initial condition of the initial problem. So their sum needs to satisfy both. U hat was satisfying the inhomogeneous boundary conditions, so v is left to satisfy the homogeneous boundary conditions. And u hat was not satisfying the initial conditions at all, so v has to fix whatever u hat has left behind. So we have a u hat that solves a second order ODE in this case. So we can write it explicitly and find a steady state solution if u1 and u2 are not 0, so the boundary conditions are not homogeneous, then you would have u hat just being a line connecting the value of u1 at 0 and the value of u2 at L.